Okay. This is some of the devices we fabricated and packaged for the different applications. Those two devices here are the basic devices which only for references. These four devices are for UV sensor application. They have different material dopant compared to others, and also the surface passivation. The majority of the devices here, they are all surface acoustic with biosensing. They are ready to put the microfluidic chambers on the top to do the measurement. They all have different IDT designs, different substrate design, and different guiding layer design, different reflector design. So they have different features for the biosensing in the liquid environment. Some of them is good for micro pump. Some of them are good for the bio-target measurement. Some of them are more balanced device. And for example, this one is a final device already connected with the impedance match circuit. It's ready for measurement. And if we take a close, if we zoom in a little bit, we can see the silver color is the IDT, and in the middle area, it's the propagation areas. That's for biosensing. It's almost 4 millimeters. It's wide enough to embed the microfluidic chamber. But the problem, along with this long propagation area device, is it have very high insertion loss. So this is why we optimized so many different design devices to solve this high insertion loss problem. Okay, in next section we will give a very simple comparison between the basic devices and with optimized devices. Thanks a lot. Now we are showing a comparison between a reference device and the optimized device. This is the transmission coefficient of the reference device. As we said before, the propagation area between the input and output IDT is very long to make sure we can put in a microfluidic chamber on it. But this long propagation area will make very high insertion loss. So we can see the resonance peak here is not sharp enough, and there's fairly prominent noise around it, which means the quality factor of this device is very low. Okay, this is one of the optimized device we fabricated by optimizing the substrate cutting angle design and adding a zinc oxide guiding layer on top of the substrate, and we use the single phase unidirection transducer for the single direction acoustic wave generation, and also we added grooved reflectors for enhance the resonance. We can see the biggest difference with the previous reference devices. The resonance peaks are all very sharp. That means they have high quality factors for the resonance, and it doesn't only have one resonance peaks. It have at least 4 resonance peaks. Actually, we can see the 5th resonance peak here, which is 3rd order resonance peaks. And different resonance peak means they are belonging to different wave spaces. For example, this is the 1st order relay wave resonance peak. This is the 1st order love wave resonance peak. This is the 2nd order relay wave resonance peak. This is the 2nd order love wave resonance peaks. The character of this 1st order relay wave resonance peaks is it can attenuate very quick into the liquid, which means it's ideal for the micro pumping application because energy go to the liquid very easily. And this 1st order love wave resonance peak, which is very sensitive to the surface mass change, but it never attenuates in the liquid environment. So that means by using a different wave spaces on the same device, we can fabricate micropump based on this resonance peak, and we can fabricate protein detection area by using a log wave resonance peak, and also the high order resonance peaks, we use them as a temperature reference signal to compensate the temperature effect. We will introduce this later. Thanks.